friction force. So we're going to backtrack a little bit and look at yesterday's PowerPoint, and then we'll build on it. So, slideshow from the current slide. If you have an object that's still and you pull on it with a little force of 2 newtons and it remains still, well, there's actually a static friction force acting on the bottom of the brick, between the brick and the table, and the static friction force holding it there would be equal to 2 newtons as well. So let's say you pull on the brick a little harder. You pull on the brick with a force of 3 newtons. And the brick still remains still. So the static friction force holding it there would be 3 newtons. So the first thing you need to note is that the static friction force depends on how much you're pulling on the object. The static friction force varies in magnitude depending on how much the applied force. What we're going to be interested in calculating is how big that static friction force can get. For example, let's say you pull on the brick with a force of 4 newtons, and that's the most static friction force you can have. If you pull with anything more than that, it's going to budge. So once it budges, the static friction force becomes a kinetic friction force, and if I just pull with an applied force with just a smidge more than 4 newtons, it finally starts to move. And the static friction turns into a kinetic friction force. And notice the kinetic friction force is much, much less than the maximum static friction force. And what we're going to do is figure out a way how to calculate this kinetic friction force and how to calculate that the maximum static friction force as well. So, notice the kinetic friction force is less than the maximum static friction force. Note, the static friction force varies. The static friction force depends on how much the applied force is. The kinetic friction force only has one value, regardless of how fast the object is moving. So let's take a look at a video showing the difference between static and kinetic friction. Okay, ready? Record. So the applied force is 10, and the static friction force holding it there is 10. The applied force is 12. Static friction force holding it there is 12. How far will it go? And it went to about 14 newtons. Notice, once it budged, it dropped down, and the sliding friction was less. So, now we want to focus in on what factors actually affect the friction force when you have a solid sliding against another solid. And before we get to the 2 factors that actually you need to know, we're going to talk about something that's not a factor, and that is how much surface area is in contact. Surface area is not a factor. Here's a computer simulation I made. And in both cases, the applied force is 10 newtons. And if that brick was moving along at a constant velocity, well, the sliding friction force then would also be 10 newtons. So it would be the same friction force in both cases. Notice in this simulation here, it's the applied force that's shown. The sliding friction force is not shown. But we know that if we're sliding that brick at a constant velocity, that the sliding friction force going to the left will be exactly equal to the applied force on the right. So the amount of surface area is not a factor. Now, when I showed you that last video, how much force did it take to budge the brick? 14 newtons, yes? So now I have a video of the brick turned on its side. Ready? Ready? It again. See, it took about 14 newtons as well. One more time. Ready? So, surface area, not a factor. So, what is a factor then? Well, the first factor I need to introduce is how much the two surfaces are actually being squeezed together. And it turns out that the normal force is always equal to how much the two surfaces are being squeezed together. And if those two surfaces are being squeezed together more, then guess what happens to the friction force? Anyone? It increases. So, the force of friction is directly proportional to how much the one object is being pushed directly into the other object. I call it how much they're being squeezed together. My own personal name, squeezing.
What was that symbol for
Together.
Indirectly proportional relationship? That fishy thing?
Yeah, that means directly proportional. So, for example, if you have a brick and the brick weighs 15 newtons, then guess how much those two surfaces there, the floor and the brick, are being squeezed together? 15 newtons. So the squeezing together force there would be 15 newtons. But if someone came along and pushed down on the brick, so the brick that normally weighs 15 newtons, has someone come along and they take like their fist and they push down on the thing. Oh, one too many fingers, sorry about that. They push down on that brick with an additional downward force of, let's say, 10 newtons. So they're pushing down on the top of the brick with a downward force of 10 newtons, and the brick itself weighs 15 newtons. How much are these two surfaces here being squeezed together right now?
It's just Sinsky.
Yes.
How much is the surface between the box and the hand? Like, what that being squeezed together? Is it 10? Or
It's 10. Yes. Yep. Good question. Right here it's 10. Because you can't push down on that box without that box pushing up on the hand with 10 newtons. Now, notice if I went back over and drew in the normal force, how much is the normal force here? I know I draw the normal force like right here, but it's really acting below, pushing up on the bottom down there, but it's usually not drawn down there. How much is the normal force holding up the brick over here on the left? 15 newtons. And over here, with the additional downward force of 10 newtons and the weight of the brick, 15 newtons, how much is the floor actually pushing up? You know, what's the normal force in this case? Again, it's usually not drawn down there, but that's really where it's acting. You know, it's drawn up here. How much is that normal force this time? I should actually make it a little longer.
25.
It would be 25 newtons. So, notice, what was the squeezing together force over here for the second object?
25.
So, the point I'm trying to make is, what is always equal to the squeezing together force?
The normal force.
The the normal force. So the official way of saying this is the force of friction is always directly proportional to the normal force. Because the normal force is always an indication of how much the two surfaces are being squeezed together. So we'll pause here.